Hello everyone, welcome back. So now we're in chapter 6, mechanical properties of materials. Now, what are we going to talk about? Well, when a metal is exposed to mechanical forces, what's going to happen to it? How much is it going to deform? We're going to learn about something called elastic and plastic deformation, and we're going to learn how these very important physical properties are measured and how we quantify those properties. Okay, so let's get to talking about stress. You might be stressed already just doing this video. Okay, it's so stupid, I gotta do it every single time. But here's the thing. This cable in this system for the ski lift, it's currently in tension. It's got this very, very tight force pulling it in both directions. Now, what you probably realize is that if we had a bigger cable, well, it would probably be able to take a lot more force than a smaller cable. Okay? Bigger cable could take more force, smaller cable can take less force. Little force, big force. But that's making it a lot more difficult on us to analyze things. Like, okay, well, I know now that bigger cables can take more force, but I don't want to have to figure out what the size of the cable is as well as material. I'd like to be able just to pick a material, not have to know exactly what size it is to begin with. So how are we going to do that? Well, we're going to more or less average out the force. We're going to say, okay, yes, you're right. Big cables take a lot of force, but if we're looking at materials, you can probably say that, okay, a wood beam, can take a whole lot more force than, a whole lot less force than a metal beam. Let me see if I can make that look like metal. Drawing skills not going to work there. And it's because of the material. So if we wanted to compare them, we wouldn't compare a giant wood beam to a tiny metal beam directly because, well, maybe the wood could take more force, but that's not very useful. What we would do instead is we would say, okay, what is the stress that each can take? Because the stress averages out that force. It's more or less the magnitude of the internal force, the intensity of the internal force. So we're going to be looking at this term stress a lot, and it's one of those equations that's very helpful to memorize. Now, another thing that can happen is we can have torsion. So right here we have some motor that's twisting this shaft, and it's allowing everything else to twist around it. And it has to apply a torque to do that. Now, if we're looking at the surface of our rod, if we're looking at the surface of it, what we'll see is that there is some sort of shear force acting at a distance from our midpoint. Shear force acting at a distance from our midpoint. And that causes a force. So our torque can turn into a force. And just like we had a stress which was tensile or it could have been compressive, that was our normal stress, we can also have a shear stress right here. The way I like to say this is shear stress is trying to cut something. It's a little harder to see with a moment, so this is when we're looking at torsion. But other things cause shear stress too, like, for example, let me see. Okay, perhaps I have two boards, and they're glued together right here. Well, shear stress is the thing that is trying to separate them. I pull here, and on that little glued spot, there is a force that's trying to tear it apart. And that force is actually parallel to my area. The area is going to be whatever is revealed once you cut it. Okay, so in the previous one, the area was perpendicular. You can see it right there. And that's normal force, or sorry, normal stress. And this one with shear stress, it is parallel. And if you want to, we can actually connect our shear stress to the moment that's being applied with that equation, where this is simply equal to the force. Okay. Now, like I said before, we had tensile stress before. We also have compressive stress. And with compressive stress, it's the same equation. However, there's one key thing to remember. If they're under compression, the force is considered negative, as is the stress. Also, if they're compressed, they typically fail a lot later than with tensile. Like initially, the way they're going to perform is going to be the same whether it's tension or compression. But compression can go a lot further. You can have a lot more compressive force then you can't have tensile in most cases. Other cases we'll see are biaxial tension, like in a pressurized tank, or hydrostatic compression, where you're getting compressed by everything. So there is a lot to go on here, and you'll see some example problems of this. So if you're kind of freaking out about it, don't worry too much. The big ones to remember are this normal stress equation and this shear stress equation right here, okay? Those are the two you're going to use the most. So that's it for this time. Thank you for listening, and I hope this helps you. Be on the lookout for some example problems to really show you how stress works. Bye-bye.